Okay, guys, slight delay there. It was, trust me, a lot longer than you'll see. I had a technical malfunction with the on-screen capture device. Anyway, I'm not even going to go into that. But when we were last here, we were talking about bell-shaped distributions. And I told you about right-skewed, left-skewed, symmetric, and bell-shaped. Something to remember about bell-shaped distributions. All bell-shaped distributions are symmetric. If we smooth something out, like a dot plot or a histogram, if it's bell-shaped, it's going to look something like that. Now, you've probably heard about that in terms of a normal distribution. We'll get into that soon enough, just not yet. But all symmetric distributions are bell-shaped. So bell-shaped distributions are symmetric, but all symmetric distributions aren't bell-shaped. For example, if we have a dot plot that looks like this, that's clearly symmetric, because if I draw a line down the center, what I see on the right-hand side is equivalent to what I see on the left-hand side. It's a mirror image. That's the definition of symmetry. Bell-shaped and symmetric is symmetric. Oh, I'm sorry. Bell-shaped is symmetric, but this symmetric distribution is not bell-shaped. So, long story short, I don't want to make this too complicated because it's not a major focus right now, but something we need to know is we need to know when we see one of these dot plots or histograms, as I'll illustrate here in a few minutes, how do we classify? Well, guys, it's if there's a tail like there is up here, it's going to be one of the first two. And symmetric, as I've just explained ad nauseum, probably falls down here. Well, guys, whatever direction the tail is going, whether it's going to the right or going to the left, defines this distribution. So, guys, this distribution right here would clearly be a right-skewed distribution. And you're probably sitting there thinking, seriously? All of that for all that? Yeah, unfortunately. Okay, I want to illustrate on R how we can do dot plots. Well, I'll tell you what. Let's get into histograms a little bit, and then we'll jump into R in just a second. Okay. So, to do a histogram, we'll just use the data that we had before, the frequency distribution for the points scored per game. And the way this would work out is we would set up a horizontal and a vertical axis in this case, and we would probably run our bins. Our bins are just the way that we break up the frequency classes on the bottom. We want to break it up to where we have 7 or 8 classifications. Now, guys, let's think it through. Our data arranges from 11 to 20. And if we want to divide this into approximately 7 classes, then we're making from 11 to 20, we're making a change of 9 units. And we want those 9 units to be spread equally over 7 classes, then we're looking at approximately a change in 2. It's about 1.2, something like that, but as it rounds up, we'll be about at a 2. So what I would probably do here is I would come in and break this up and start at an 11, and go up to a 13, and go up to a 15, go up to a 17, go up to a 19, and then go up to a 21, which is as far as I would need to go because we had cases of 20. Now, if I go back to my data that I had previously, let me bring that back up, and look at the frequency distribution, which I had. I can't seem to find it right now. But that's what happened when my video went crazy on me. But we can see that from 11, now let me explain what this means, 11 to 13. This means that we start at 11 and go up 2, but not including 13. This would be 13 and 14 up to 15, but not including 15. So from 11 to 13, we need to see here that we have 4 pieces of data. from 13 up to 15, but not including 15. Whoa, isn't it comforting that your statistics professor can't count? We have 6 pieces. For this, 15 up to, but not including 17, we're going to have 1. And then from 19 to 20, we're going to have 1. So I can see that the highest frequency that I have in any class is going to be 6. So what I would need to do over here is I would need to do my counts to accommodate 6. Now let's say I had a data set that had 100 and my biggest frequency within a particular class was like 17. Then I would need to accommodate that according to the way I do this. Now, the good thing about it is you're typically going to create these with technology, and it's all going to be done for you. So guys, I know that I have 4 pieces, 4 scores, 11, 12, 12, 12. So I need to run this up to about 4. I need to run the 13 up to, but not including 15, up to 4. 15, but not, so that's just going to be a 1. And then this one will be a 1. Now guys, you can still see that we have kind of a distribution that is right tail. Which gives us a right skewed distribution. Now, times like this, it's so tempting. And guys, I know because I've been a student for many, many, many years, I don't get to run my mouth for a living teaching this stuff without having spent a lot of time as a student. It's so tempting because, you know, when this gets really, really easy, to say, I'll figure it out. I don't need to watch, I got better things to do. I need to be on Facebook or Snapchat or something cool. I don't need to listen to Darbo's stuff. What will happen then is you're going to miss stuff. And you'll send me one of those emails and you're like, well, what video was this covered in? I don't remember you covering this. Well, don't do that, okay? Just hang in there with me. Well, I'll try to make this as quickly as possible. Now, what we sometimes want to do is we want to change the frequency axis to a relative frequency axis. And all we're going to do there is we're going to take the same graph that we just created. Now, notice from 11 up to 13, but not including 13, we had 4 observations. From 13 up to, but not including 15, we had 4 observations. We had a 1 and a 1. Now, relative frequency, and guys, hold on just a second. I need to grab my calculator. All right, sorry about that. I was just videoing on the back room, and then when I had computer issues, I moved to the front room. Okay, so what I've got here, relative frequency just says relative to the entire group of data, what percentage of the observations are between 11 and 13. So guys, what I do there is, again, I have 4, 8, 9, 10. I have 10 observations. So I know that 40%, actually it turns out I didn't even need a calculator. I thought there were 11, and I was going to have to do a little bit of calculator use, but it turns out I didn't need that. So I have 40% here, I have 10% here, and I have 10% here. Okay, and this will always add up to 100%. A relative frequency histogram does exactly the same horizontal axis. So we'll break it up. Up to 21, But now, instead of focusing on the counts, the frequency within each particular class, we're going to look at the proportion, or the relative frequency. So 40% of the observations were between 11 and up to, but not including 13. So I have 40%, 40%, 10%. So what I would probably do if I were creating this by hand, and again, by the way, I never would. I'd always use technology, and I'm going to demonstrate that in just a second. My reason for doing this by hand, I think you have a better understanding of these things when we run them through and create them by hand, at least sketch it, than just letting technology do it and assuming we've got it all figured out. So I would bring this up to the 0.40, and I bring this up to the 0.40. From 15 I have 0.10, and then from over here I have 0.10. So guys, it doesn't change the shape. We still see the same thing. We still summarize it the same way, but it's just a little different way of creating the information on the vertical axis. Why did I cover that? Well, I covered it because there's a couple of homework assignments that works that way. Now, guys, this is going to be a kind of a crazy because we know the numbers. Now, pretend we don't know the numbers. And that's the way it'll happen a lot of times. We won't have, sometimes 1,000 numbers. We'll just have a picture that summarizes the 1,000 numbers. But what I want you to notice is this distribution, or this part right here. If we didn't know that these were basketball scores and these were maybe ACT scores, maybe for 7th graders, which you would assume, to score lower because they haven't had a lot of the material that's been covered. But let's say we had a distribution like this of ACT scores, and all someone told us is we have 1,000 students whose ACT scores we're representing in this graph. Well, and someone asks you, what's the highest score? What's the highest score of these 1,000? And someone asks you, well, what's the lowest score? Well, what I know, because the way ACTs fall on either 19, 20, 21, I know that this bin right here tells me that I have 10%, so approximately 100, 19s or 20s. So what's the highest? Well, it's tempting to say 20, but you don't know that. You just know that 10% of the data, again, it's 19 up to, but not including 21. So the way this is measurements. You could have 19 inches, 20 inches, 19.5 inches, 19.25 inches. But since we're dealing with ACTs in this hypothetical example, it has to fall on 19 or 20. Was there a 20 in here? Well, we don't know. There could be 119s, in which case we would draw this last rectangle the same way. Maybe there's 19s and 20s. We draw it the same way. If the combination of 19s and 20s is 100, 10% of the 1,000, or if all 100 of those are 19s, this last bar is going to look the same. So the highest, well, 19 or 20. What's the lowest score in the observation? It's tempting to say 11, isn't it? We don't know that. If we had 40% of 12s, let's just say we had 400 12s, and the 401st was a 13, then it's going to be 12. That bar is going to look the same. Let's say we have all 11s, or half 11s and half 12s. That bar is going to look the same. So it doesn't give us, the proportion of scores within that class. It just tells me that 40% of the data that I collected is an 11 up to, but not including a 13. So it's an 11 or a 12. So what's the score? The smallest score? Well, it's either an 11 or 12. I don't know. Can't get that information. Now, a lot of people want to tell you, well, that they can look at these things and get an average. Well, you're smarter than me because I can't do that. I can sit here and say, well, it looks like to me the typical ACT was somewhere around a 13. But I can't give you an average. I can't give you a standard deviation. I can't give you all those fancy numerical summaries. And we don't need that. Guys, that's not what we're all about at this stage. We're just about seeing the distribution. What kind of pictures or what kind of graphs are appropriate for the type of data that we have? And then once we see it, how do we classify it? Right skewed, left skewed, bell-shaped and symmetric, or just symmetric? You know, how do we do that? Now, I want to give you a couple hypotheticals here, and I want you to tell me. Well, it's going to be kind of hard to tell me because you can't talk to me. But let's predict the shape of the distribution. Now, guys, these can be tricky. Okay, they can be really, really tricky. But let's just say the shape of the distribution, if we were given you know, a large set of values. So, guys, the first one I want you to think about is the number of speeding tickets for SSU students. What would that look like? Now, you probably think, if you're one of these impulsive thinkers and you've got to have something just said, you know, if you can't answer it in 0.4 seconds, it means you're stupid. That's stupid to think that anyway. The smartest people I know say I don't know more often because they think things through. They persevere. They're patient. They think it through. Impulsive thinkers, they usually don't have high-level positions because people want, you know, they want things, people to think things through. It's some of the issues I have with some presidential candidates. If I'm going to be honest, I'll never get political with you, although maybe I just did. I like people to think things through. The scope of the importance of the decisions that the President of the United States has to make. Hey, I want them to surround themselves with good people and sit back and think about things before they answer impulsively. Now, who's it apply to? Well, you figure it out. I don't know. Maybe multiple candidates. All right, back to speeding tickets, although presidential stuff's more fun. Number of speeding tickets for SSU students. Well, what would it look like? Let's think about it. You go up and stop Bill. Hey, Bill, what's up, man? How many speeding tickets do you have? I don't have any. You go down the hallway. Hey, Mary, how many do you have? I got one last year. Bill's brother, how many do you have? Man, I tell you what, they get me all the time. I got 4 of them. The other one, I haven't had any, and I haven't had any. So if you did that for all approximately 3,500 students, 4,000, whatever our enrollment is now, or it's going to be when you're watching this video, what would you think it would look like? Well, I would think that we'd have a lot of zeros. And I would think we'd have, you know, quite a few people with 1s, but probably not as many. Probably not even half, so that bar may be a little bit higher. 2s, I doubt very seriously there's many, but you know there's some. Poor old Bill or whoever, you know, he had 4. I don't think there's many students at Shawnee State University that have had 4 speeding tickets. And you know, let's say we're doing this over the last year. So guys, what would you think here? I would think right skewed. All right. That was so much fun. Let's do the next one at age of death. So let's say that you're doing age at death in a large city. And I don't know if you've ever looked at the obituary or not, but in a large city, but you know, most people who pass away are older. So I would think if I was doing age at death, I would want to look at this not from zeros 1, 2, 3, 4, because I'm going to have probably those responses. I would probably want to look at this in classes I really don't know how far to go out, but let's just, for the heck of it, let's go out to 100. I think anyone who lives more than 100 would clearly be an outlier. So where do you think the tallest bar is going to be? Well, guys, I'd say more than likely the tallest bar is going to be around 70. certainly, you know, quite a few people die between 80 and 90, and some people are lucky and live more than 90. And I'd say quite a few people between 60 and 70. And clearly some between 50 and 60, and some between 40. And you know, you would think that these bars would decrease as we come this way. So guys, as we smooth this out, and you know, clearly, again, unfortunately, we have deaths down here. So we smooth this out, what would we expect to have? Well, I would think we'd have left skewed. Okay, I think that's reasonable. Now, did I know the answer to this one before I did this problem? I just kind of chose this from a textbook. Did I know the answer? I didn't. I hadn't really thought about it, but as you think it through, it makes sense. Had I thought about this one? Yes, I thought about this one before, so I kind of was prompted on it. And the one I'm getting ready to give you next, I've kind of thought about too. So, flipping a coin. And let's say we flip the coin 5,000 times. So we flip it one time, we get a head. Flip it again, we get a head. Flip it again, we get a head. Flip it again, we get a tail, then we get a head, then we get a tail, yada, yada, yada. And we count this. How many times did we get a head? How many times did we get a tail? What do you think this would look like? Well, guys, it would probably be about the same number of heads and tails. So we would have a symmetric distribution, but it clearly is not a bell-shaped and symmetric. So just symmetric, but not bell-shaped. Bell-shaped. I'll tell you what. Let's do one more. This is, you know, having so much fun here. All right, let's say Dr. Darbra, Dr. whoever comes in and gives you a really easy test. What do you think the results would look like? Okay, let's say I don't know, because we don't, but we certainly can think it through, and we can kind of get an indication of what we think it would look like. So again, scores usually range from 0 to 100, so I think it would make sense, instead of writing out, you know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think it would make sense to make up the axis this way. All right, well, this shouldn't be a 1,000, it should be a 100. So what would you think? Easy test tells you what? Scores are high. Because I would think that there'd be a lot of scores between 90 and 100. Quite a few scores between 80 and 90. Quite a few scores between, but I wouldn't expect many low scores, although, you know, there's going to be a couple of people that aren't going to come to class, they're not going to watch videos, they're not going to do stuff that I ask them. So I'm going to say that an easy test would look something like this. Smooth it out, think about the tail, left skewed. And I think it's easy to conceptualize this, or at least generalize that if we had a hard test results, that we would flip that and get a right tail distribution. So gang, what do you think? See and summarize. And so far we know that if we have quantitative or numerical data, what are the two graphs that we're going to use to see and summarize the distribution? Well, we want to look at a dot plot, and I'm not a big fan of dot plots, so taking a class from me, you're not going to get much on those, and I'm going to illustrate in R why that's the case. But a histogram, these things are extremely important in displaying quantitative data. Okay? Now, what I'd like to do is I'd like to demonstrate some of this. Now, the first thing I want to do is I want to show you how to do this on your calculator. So what I want you to do, if this is the first time using your calculator, and what we'll do, I'll demonstrate doing a histogram with the point, the points that we did earlier the 11, the 12, the 12, you know, so on. So we'll use that as a demonstration. Okay, guys, if it's the first time using your calculator, what I want you to do, I want to get everyone started with no bugs in your calculator. So right here you've got a memory button. It's blue, which tells me I've got to hit that blue button right there. If your memory is yellow, then you've got a yellow button right there. You need to hit it first. So I want to hit the second memory. And I want to come in and I want to reset my calculator. Now, guys, if you've got, if you're a programmer or something and you've got some really cool things stored, you don't want to do this. But most of you, it's going to be a lot easier for you if you'll do this. That way, we're going to get started on the same platform, and these minor errors that students encounter are going to be minimized by doing this. Okay, so I want to reset. I want to reset. I want to reset all RAM, and I want to come down to reset and go for it. Let's hit a clear. Now, guys, right here you're going to see a stat button, and we're going to wear the paint off of that button for obvious reasons. It's a stat class. So I'm going to hit it, and the first thing you see is that I've got an edit, calc, and test option. And what I want to do is I want to go to edit, because that's where I go to edit data or to enter data. Now I'm going to enter my data, so I'm going to enter an 11 and hit enter. I'm going to enter a 12. And what I have, 3 12s. So enter 3 12s. Looks like I have 4 13s. So 1 13, 2 13, 3 13, 4 13. And then I have a couple of 14s. And I have a 15. And I have a really good game at 20. Now, if I want to use my calculator to get a histogram, here's what I do. Right up here, you can see where we have stat plot. Stat plot feeds off of the numbers, well, in some situations, it feeds off the numbers we put into stat. So again, this is blue. Tells me I got to hit the blue key first. First thing I want to do is select it, so I hit enter. The next thing I got to do is turn it on. And you notice right now it's turned off. So if it keeps turned off, you're not going to get anything. So I need to select enter to turn it on. And I come down, I come over to the icon for histogram. And guys, I've got to hit enter to select it. Now, the beautiful thing about taking this class online and learning this through a video is you can pause me, rewind me. I'll be here at midnight tonight or 2 a.m. whenever you want to go over this. I'll be here. If you take it from a class, you know, in the classroom, in a face-to-face setting, this is kind of difficult sometimes because professors tend to go a little faster. Well, enough said. So hit enter. Now, XList L1, that's where I put my data. So, and again, if you go back to stat, you can see the heading was L1. All right. Now, guys, some of you, if you do what I'm okay, again, frequency should be 1. And it should be reset to 1. Now, if some of you do what I'm getting ready to do right here, you might have a problem. So, some of you won't, but just to make sure that no one has a problem here, I want you to go back up to the on button and then do what I'm getting ready to show you. I want you to hit zoom. And if you scroll all the way to the bottom, you will see a function that says zoom stat. So let's go zoom 9 or just hit enter. And what it'll do, it'll create a histogram. Now guys, it broke things up a little differently than we do. It's a machine. It has an algorithm behind the scenes that breaks up the way that it sets up your classes. I would have set these up reasonable between 11 to 13 and 13 to 16 and 15, just like I did. But it didn't. In fact, you can come up here to trace and you can see that what it did is it broke the first class up from 11 to 12.8. Well, 12.8 wasn't a possibility, so I just decided to run it up to 13. So it tells us that there are 4 observations. 4 observations between 11 and 12.8, or 4 between 11 and 12. Going over, you can see that we have 6 observations from 12.8, which doesn't apply here, so it really means from 13 up to 14.6, so 13s and 14s. So again, the calculator just does that. Calculators calculate really well, but calculators don't make good common sense decisions like we sometimes need. Well, like we often need in statistics. All right, gang. I want to do some stuff for you in R, and I need to find. I had something laid out here that I wanted to show you, and for some reason I've lost my. I'll tell you what, I really got offline when my computer on the back messed up, got me off. Okay, guys, let's get out of this. So I'm going to hit escape and just close this down. And what I want to do is I want to bring up R. And I want to go to, let's go to, well, I'll tell you what, I've got Blackboard up here. Go to Blackboard and go to our site. And let's go over to content. And maybe since the last time you were there, I have data sets for R that I put up. And what I'd like for you to do is I'd like you to open up the IQ read. So guys, if you just click that, it's going to, and at least for me, it's going to come down and open it up at the bottom. Yours could go to downloads. I mean, you know your computer. So click this. And here's the download that I have. Now, the reason I like this and the reason I chose this for the illustration is it's got some quantitative variables. These are reading scores, these are LSS, ACT, IQ, estimated reading level, and it's got a couple of categorical variables, gender and school district. So it's got a little mix of both. So you've seen this before, but I'm going to go through it again. I'm going to go up and do a save as, and I want this to be IQ read, but I want it to go to my desktop. And I want it to be in CSV format, which it should already be. So I'm going to save that and hit continue. Now you can see over here on my desktop that it's saved this IQ read as a .csv. So that's cool. I don't need this anymore, so let's get rid of it and say don't save. Now the first thing I have to do is I have to set my working directory. So I'm going to get my working directory to see what form it's in. And then I'll set my working directory according to that. So I need a backslash ddarbro, and then whatever is after ddarbro needs to be changed as desktop. Now it could be downloads, it could be documents. It needs to be set as desktop. Okay, now I can go get my desktop. Whoa. Oh, gosh. I'll tell you what, I had a phone call coming in. I was trying to see. Okay, so data, read.csv, IQ read.csv is, we've read it on our desktop and we've imported it into as data. Now what I have to do now is I have to attach the data, and I always like to see the variable names of the data. And I can see that I have read LSS just like I did before. Now, what have I done here? One thing I've done is I've done a dot plot previously by hand. Now, if I want to do a dot chart of, for example, gender, well, that makes no sense because dot plots are for quantitative data. Gender is categorical. Be patient. I'll show you how to do that in just a second. Right now, if I'm doing a dot plot, I use the command dot chart, and I could do a dot chart for read. And this is what we get. Guys, this is precisely the reason that I don't like dot plots. Dot plots are really, really, really good when we have a lot of repeated data. For example, you know, I have 11, and I had some 12s, and I had some 13s, and I had some 14s, a 15, and a 20. But guys, for this information right here, you know, I have 20s and 21s, and there's just too much spread there. So a dot chart really doesn't do much good for us. Dot chart for LSS, to me, meaningless. Absolutely meaningless. Dot chart for ACT. Okay, now it kind of helps us out a little bit, but the way R does a dot plot is kind of wacky because this should be brought down to the bottom. It gives us kind of a running frequency, a running proportion. So, guys, I just don't like dot plots that well. I really don't. I like histograms much better that we've looked at before. So if I want a histogram for read, I can easily get one. So how would we classify this? Well, I would say it's left skewed. Seems to have a tail going to the left. Histogram for LSS. That's a tough one. That's kind of a right tail. Histogram for ACT. That's a strange one. Okay, I would probably call that a left tail. Saw it. And a histogram for IQ. I would probably call that, gosh, almost symmetric. What I would say here is that the typical score seems to be between 100 and 110 because the bar is the highest. The typical score for ACT seems to be between 19.5 and 20. So we know that has to be a 20 because an ACT can't be 19.5. So again, this thing is read as 19.5. Well, actually, they're doing it different here. So it's 19.5 up to and including 20. So it does it slightly different. Okay, guys, really, you know, I can't make this stuff hard if I really tried. That's you know, just being able to create a dot plot and summarize it. Histograms. Also, we can create histograms with our calculator, or we can create histograms with very, very easily with R. Now, one more thing. Let's say that I didn't want to have this in a .csv format, and I just wanted to type in the data like I had from the beginning of the video. What I could do is I could create something, let's call it points. And I could use the C function, which I have to do anytime I'm entering raw data, raw numbers into R. So here I could do use C and just type these things in like I did in the calculator. And you know, I could do a histogram to find out how many I've got, how many numbers I have. You know, I should have 10. You use what's called length command of points, and 12. I did have 12. Guys, I messed up earlier. I said I had 10, so. Go back and change the relative frequency to 12. So I messed up big time there, didn't I? Shoot. Well, that'll probably drive me crazy. I may end up redoing this video, and you guys will never see it. But gosh, how did I miss that? That's awful. Statistics professor can't even count. Goodness gracious. Oh well. If that's the worst mistake I make this week, I've had a pretty darn good week. All right. All right. So if we want to do a histogram, I could just do points because this is what I am calling these these numbers that I entered, and you can see that we get the following. Now, again, from 10 to 12, it does a little bit differently here. It goes from 10 up to 12, including 12, and this goes 12 up to 14, including 14. So that's tricky stuff there, you know, just depending on the technology. So, all right, guys, let's go over to gender and school district. Let me show you how to create a pie chart and a bar chart. So again, if we have quantitative variables, then a dot plot and or histogram is appropriate. If we have categorical data, a pie chart and or a bar chart is appropriate. All right, so we have gender and school district, our categorical variables, and EST and so on are quantitative. So if I want to do a pie chart, it takes a little bit more to do a pie chart with categorical variables. There's not just something like histogram. We could just type it in and go for it. So what I would have to do here is I would have to do X tabs, and I would want to do a tilde, and I would want to get a feel for gender. So what I see here is I have 12 females and I have 18 males. So I'd like to create my pie chart accordingly. So what I'm going to do is I'm going to just create a kind of a variable X, and I'm going to put these counts for 12 and 18 for female and male. The next thing I'm going to do is I'm going to create my labels for each one of these. Well, since I put the number for females first, I'm going to put female, and then I'm going to put male. Yeah, guys, once I get this set, I can just do a pie chart with X labels, and you'll get a real pretty pie chart that you can copy, paste, put into a document, and represent the percentage proportion of females versus males. Okay? So because more of the slice of the pie is given to males, it tells you that more males are included in this hypothetical data set. Now, if I wanted to do the same thing for school district, all right, so what would I do first? I would want to do X tabs, tilde, school district. Well, if I could spell it, probably would help. So I have 7977, so I would probably set this up as, you know, something else, X1, let's just call it. So I would have, let's see, C, so I would have 7977. And then I would need to see what my labels are, which is given to me right above. So I would call this labels 1. So I would call that northeast, northwest, southeast, southwest. So now we'll come in with pi, X1, labels 1, and I would get a pie chart. It represents the distribution, if you will, the variation in the school districts for these kids. So most of our school kids came from the Northwest School District. Kind of a tie on Southeast, Southwest, and and northeast, of course. But we knew it was 7797 from the X tabs. Now, a bar chart is something that's also pretty easy to create, but the first thing you have to do in a bar chart is create a table. So I'm just going to call this gender table because I'm not that creative to begin with. And I go in with the table, and I'm going to create a table for gender. Next thing I want to do is do a bar plot, and I want to put the name of the table in there, and you can see we get a table. It kind of looks like a histogram, because the big difference between a histogram and a bar chart is the bars do not touch in a bar chart. That'll be one of those questions. It probably won't show up on my math lab, but it'll show up in your midterm, and you'll say, well, I never saw that on my math lab, and that's well as on the videos. You need to watch the videos. So, gang, if we want to do the same thing for the the school districts, I would create another gender table, but this time I would call it not gender table, but district table. And I would change this to school district. And then I would do my bar chart or bar table. And you would see that I get a bar chart for school district. Guys, what I want you to really know, I want you to know how to use R, how to use your calculator to get a histogram. I want you to know how to use R to get a bar chart, a pie chart for categorical variables. And I want you to know how to use R to get a dot plot. Although, guys, you won't see me use dot plots much because I don't like them. But they do. If you create them by hand, they seem to work. But I just don't like the way technology does a dot plot. But the main thing I want you to know is, first of all, when we think about creating pictures to display variation, we see and summarize. Create the graph to see the picture, and you summarize it with ways that we've talked about in this video. The next thing I want you to know is what you use to see and summarize depends on the type of data that you have. If you have quantitative, numerical data, then swear I can type. I just can't. I'm sorry. I promise you I can spell. I just can't type. And if you have categorical and what we call qualitative data, then you're going to use a pie chart and or a bar chart. So guys, what's the difference between a bar chart and a histogram? The bars do not touch on a bar chart, and the ordering of the axis is irrelevant. If I go back up here and look at one of these histograms that I created earlier, for example, of something, points. Let me find it. There it is. If I do a histogram of points, when I read it from left to right, there's a natural ordering. The points out here are bigger than the points down here. However, if I do a bar chart, this left to right ordering was arbitrary. So that right skewed, left skewed, right tailed, left tailed doesn't matter, because R decided to put northeast first because that was the first observation it saw in the data set. Northwest could have easily have gone first, putting the highest bar right here. So guys, that's all I got. This should get you very, very, very well prepared for some questions that you'll encounter on my stat lab, my math lab, same thing. So have a good one.